Hey, hello and welcome to today's GFG problem of the day. Hope you are doing well. So let's see today's problem, Euler circuit in an undirected graph. Okay. So what the problem is saying is we'll be given a graph. Okay. We'll be given a graph and we want to find out whether in the given graph, whether there exists a Eulerian circuit. Okay. Whether there exists a Eulerian circuit. And what is a Eulerian circuit? So before Eulerian circuit, we want to understand what is Eulerian path. Okay. So Eulerian path is nothing but it follows certain conditions. The conditions are that all edges in the given graph should be visited. Okay, should be visited. Second is, and it should be visited. All edges should be visited exactly once. Okay, exactly once the edges should be visited. For example, if we start traversing from this node, 0, right? Okay, if we go to 0 to 2, followed by 2 to 3, right? And then 3 to 1, and then 1 to 0. So if you see, all the edges are exactly are visited, right? All the edges are visited. We have covered all the edges. And they are also visited exactly once, right? They're also visited exactly once. So that means this graph is following this two property, and hence we can say there exists a Eulerian path, right? There exists a Eulerian path. Now, if you have understood the Eulerian path, what is Eulerian path? Now let's understand what is Eulerian circuit. So Eulerian circuit is a circuit wherein it follows these two conditions of Euler path. Along with that, if we start from one node, right, and we should reach to the same node again. That is, the start and end node should be the same. So in this case, if you see, right, in this case, if we started from this node, right, so we visited 2, 0 to 2, then 3 visited, then 3 to 1, and 1 to 0. So we started from this 0 node and we are coming back to the node 0. Okay. So the additional condition is that the start and end nodes should be the same. And hence, if a certain graph follows these three properties, then we can say there exists a Eulerian circuit. Okay. For example, let's take another example, 0, 1, and 2, right? So if you see, let's say we start from this node, and if we go to this node, right, it ends over here, right? It ends over here because there does not exist a path, right? So we are not able to visit all the edges, right? We are not able to visit all the edges, and we are not also able to come to the start node again, right? Definitely we can come, but all the edges are not getting visited, right? Because there's no connection over here. Okay, so we can say that this graph does not follow the Euler, does not contain the Eulerian circuit. Okay, does not contain the Eulerian circuit. Now quickly, how to solve this problem? How to solve this problem? So if you've understood the problem, I would suggest you to subscribe to my channel. Now let's look into the intuition, right? How to solve this problem. So let's draw this graph again, right? 1, 2, and 3, right? So it's all about observing the pattern in order to solve this problem. So if you see, if you closely look, right, how can we say that a graph contains a Eulerian circuit? How can we? Yeah. So what we can do is, see, if you observe, right. So what is the? So if you see, what is the in degree of each node of this zero node? What is the in degree? So the in degree is 2. That is how many edges are coming towards 0, right? So if you see 1 and 2, right? If you see, there are two edges which are coming towards 0, right? Then if you observe this, let's consider 0, 1, 2, and 3. These are the vertices, right? So how many edges are coming towards 1? So again, there are two edges, right? 0 and 3, right? How many edges are coming towards, for example, 2, right? So there are two edges coming again. So 0 and 3. How many edges are coming towards 3? There are two edges, right? 1 and 2, right? So if you observe this graph, right? If you observe this graph, so we saw that there exists a Eulerian circuit. Now, if you observe, what is how it is following? For example, now what is the in degree? That is, in degree is the number of edges coming towards that particular node. So in degree for 0 is 2, because there are two edges which are coming towards 0. If you see, the in degree of 1 is 2, right? If you see, the in degree for 2 is 2 again, two edges coming. For 3 it is 2. So if we see, if there is a graph whose every node has even in degree, okay, that means there exists a Eulerian circuit. So if you look at this particular graph, right? If you look at this particular graph, what is the in degree for 0? It is 2, right? Two edges are coming, right? What is in degree for 1? It is 1, because only one edge is coming, right, towards 1. It is 1, right? What is in degree for 2? It is 1 again, right? So if you observe, right, so in this case, all the vertices did not have even number of in degrees, right? Even in degrees, it had odd in degrees, and that is why there does not exist a Eulerian circuit. Okay, so this is a observation. For example, let's extend this particular graph, right? For example, let's add few more vertices. Let's make it a bit complicated. So here, if you see, now what is the integrity for 3? Let's first see whether there exists a Eulerian circuit or not, right? Eulerian circuit. For example, let's start from this particular node, right? Again, we go to 1, then we go to 3, we go to 5, then we go to 4, we go to 3, we go to 2, and we go back to 0. So yes, we are like following all the conditions. We have visited all the edges exactly once, right? Exactly once, and we have come back to the same node where we started. Okay, so that is why there exists a Eulerian circuit. Now, if you look, now what is the integrity for rest? So for integrity for these 3 nodes, they remain same, right? But 3, it changes. So 3, how many nodes are, how many edges are coming? 1, 2, 3, and 4. So the integrity is 4 for 3, right? So if you see, right, there are 4 edges, right? So integrity for 3 is 4, right? And if you see for 4 node, what is the integrity? 2 nodes, two edges are coming, right? So again, integrity for 4 is 2 only, right? For 5, again, two nodes, 2 edges are coming, right? So integrity for 5 is also 2. So if you see, right, so if there is a graph where for every node there is even in degree, right? There is even in degree, not the same, right? So even if 3, it had 4, and rest nodes have 2, right? So if there's a graph whose every node has even in degree, then we can say that there exists a Eulerian circuit. If it is not the case, then there is no Eulerian circuit. Okay, I hope you've got the intuition. Now the implementation would be very simple for this. Okay, before going to the code, I would request you to subscribe to my channel, like the video if you have got the intuition. Thank you so much. Now let's see. It's a simple code. First, I'll show the Java code, followed by C++. Okay. So what we'll check, whether every node has even in degree. So it would be pretty simple. Adjacency.get I, right? Get I, right? For each node, we are checking the size, right? We are checking the size. If it is odd, then we'll simply return false, right? Wherever for any node, if we return odd number of size, then we're going to return false. Otherwise, we are going to return true. Okay, if you have a look at this, so we are calculating what for every node, right? For every node, for every I is node, right? I is vertex. For every I, we are checking the size. So here, what we are checking? The size, right? So for every node, what are the number of vertices here, right? It would be 2, right? So this is the size of this, right? So we are checking the size, right? If it is odd, then we are going to return false, else we are going to return true. Let's submit this. Okay. Yes, the test cases have been executed successfully. Okay, what happened here? Let me rerun again. Don't know why it is being like that. Yeah, now it accepted. I don't know why it got TLE, but no problem. So this is a solution. I hope you have got the solution. I would request you to subscribe to my channel, like the video. And also one quick thing, definitely I'm going to show the C++ code. It's almost same. But here, the time complexity is what? The time complexity is O of V, right? Because we are traversing all the vertex, right? And what is the space complexity? It is constant only, right? Because we are not using any extra space. We are not using any extra space. Okay. So let me quickly go to the C++ code here. Okay. So here is the C++ code. So it's simple, almost same, right? So we are doing the same thing for, we are calculating the size. We are checking the size. If it is odd, then it false, else true. Okay. So yeah. So this solution. I hope you have got the solution. Thanks for watching. Have a happy, healthy, and a great day. Thank you so much.